Okay, so on LoRaWAN antennas. He's an associate professor at the University of Côte d'Azur in France, of course. Ladies and gentlemen, please welcome Fabien Ferrero. There you go. He pointed over there.
Perfect. Okay. I'm really glad to be here. So my presentation is entitled The Challenge of LoRaWAN Antenna. So why designing antenna for LoRaWAN is challenging? I think most of you have started to design M2M system using, for example, Zigbee or Bluetooth. And antenna was not so important for this type of technology. So why? First, because, for example, Zigbee is using 2.4 gigahertz bands. So it's 3 times the bands you are using for LoRa. And also, it was technology with quite a short-range communication capabilities. And when you are thinking of LoRa, LoRa is long-range. So there is a strong expectation to have long-distance coverage with this technology. But LoRa is also using sub-gigahertz band, so near 900 megahertz. And at 900 megahertz, the wavelengths start to be very large. It's close to 34 centimeters. So here is the outline of my presentation. I will start to give an example to show you that the choice of the antenna can be very important. So a practical example. So then I will show you some antenna key parameters and 2 projects, a low-cost open source project and a more industrial project, which is a micro tracker. And I will finish by conclusion, some perspectives. So here is the project. So it's a smart farming project which was conducted by my friend Conductive from University of Po in Pakistan. The idea was to have humidity sensors in cornfield. So you know that corn can be very tall, about 3 meters. So the idea of Conductive was to say, okay, I will sense the humidity, so I have to have sensors very close to the ground, and I want to transmit. So I will go high, and I will use some mast, okay? And I will have a cable between the sensors and the antenna. And you use a quarter wave antenna placed on the mast. And you do some tests, and you get just 1 kilometer of coverage. So he was really disappointed. So we discussed, and I explained to him that when you are using a quarter wave antenna, usually you need a ground plane. I mean, not usually, you need a ground plane. And to explain what's happening in this case, I do electromagnetic simulation. So you can see here the radiation pattern you get if you do the simulation of quarter wave antenna with a cable. And you see that it's not really not what you want. Usually a dipole has a strong pattern toward the horizon. And here, if we look at a cut, you see you have some, okay, not working so well, but you have a null that appear in the horizon direction. So when you have this type of nulls, you are losing a lot of communication capabilities. So the gain in the horizon, where is the gateway, is reduced to minus 40 dBi. Normally, for a classical dipole, you should have 2 dBi. So this is why you get so small communication range. So why do you have this effect? Is because if you are feeding a quarter wave antenna with a cable, and you are not using a balloon, you will have a lot of current which will flow on the shield of the coaxial cable, and it will form, in fact, some antenna array all around the coaxial cable. And with antenna array, we can have some destructive interference toward the horizon. This is exactly what we get here. So he replaced the quarter wave antenna by a classical balanced antenna with like a dipole with a balloon, and he get 20 kilometers of communication distance. So it was just a practical example to show you that it's very important to choose the right antenna, or you can have a lot of disappointment. So I'm going to some antenna key parameters. So just to be sure that we are talking about the same thing, I will just give you some few definitions. So PS will be the power which is transmitted by the source. So for you, the source will be the LoRa chip or the LoRa module. Then you know that if you have a different impedance between your antenna and your chip, usually your chip is 50 ohm, you will have a part of the power which will be reflected. And this will be here Pref. And also we will have PRAD, which is the radiated power. So this is a useful power that you need for your communication. So the indicator I'm going to use, the first one is the reflection coefficient. So a reflection coefficient is the ratio between the power reflected over the power which is transmitted from the source. So, of course, usually you don't want to have any reflection, so you want this value to be, this parameter to be equal to 0 in linear or minus infinite in dB. So usually we plot the reflection coefficient or S11 in dB. So classical criteria for this parameter is minus 10 or minus 6 dB, it depends on the application, which give 90 to 75% of transmitted power. The second important parameter is total efficiency. What is total efficiency? It's really the efficiency of your antenna. So it's the ratio between the useful power, the radiated power, and the power you send from your source. So it includes then the matching losses and also the radiation losses. And it can be plotted in linear on dB scale. And usually we expect to have something between 30 to 70% of total efficiency. And then you have the gain. With the gain, it's a little bit more complex to understand because it will include the matching, the radiation loss, and also the directivity. So maybe you have already heard about directivity. The directivity is the idea that an antenna is capable to focus the radiation in one specific direction. So you have to imagine an ideal antenna, which will be lossless, and also this antenna will be able to radiate exactly the same amount of power in any direction. This antenna is named isotropic lossless antenna. And when you are talking about gain, you are comparing the power density of your antenna with the power density that will be radiated by this perfect lossless isotropic antenna. So the gain can be positive or negative. If it's positive, it means that you are able to focus the energy in one direction. So antenna is only passive. You cannot create energy. So it's really just focusing of the energy. And usually it's plotted in dBi. I is for isotropic. So antenna is a resonant structure, so meaning that the input impedance is changing with frequency. So meaning that you will have a limited operational frequency. And miniature antenna also can have low efficiency due to the metallic and dielectric losses. So usually we use this triangle to say that you will have to when you are doing miniature antenna, you have a trade-off between efficiency, size, and bandwidth. The second important point is antenna is an open structure. So if you compare with classical electronic components, antenna is strongly influenced by all the surrounding environment. Because you have to imagine that your antenna is not only the metallic wire that you see on the antenna, but it's also all the invisible field, so electric and magnetic field that appear all around the antenna. And if you disturb this field, you are changing the characteristic of your antenna. So for integrated antenna, the EM wave, which is radiated, is generated both by the antenna and also by the terminal ground plane. So we'll see this after. So very important thing: the small antenna have to be very carefully tuned. And when you are looking to IoT application, we are adding more constrained than the triangle I showed you before. So, of course, you still have the bandwidth, efficiency, and size, but you have also additional constraint, which is the directivity, because you have a lot of application where you want to have some directivity. Take, for example, wearable application. You don't want to radiate towards the body, because you are just going to lose your power. So you want to be able to radiate in a specific direction. And also, one important parameter is the sensitivity. You don't want that your antenna is too sensitive to the environment. If you place it on a metallic table or on a wood table, you want to have always the maximum performance. So you are adding a lot of additional constraint. How much can I irradiate? So regulators define the maximum power that you can irradiate. It's defined usually in equivalent radiated power, so ERP. In Europe, ERP at 868 megahertz is 14 dBm. So what is ERP? It's the amount of power applied to a half-wave dipole to give the same power density at the given point. So meaning that the regulator is saying you can radiate an ERP of 14 dBm. So if I'm using a dipole, so it's the first one, so a dipole has 2 dBi of gain, so I can use my output power of 14 dBm. Now, if I want, for example, to use a more directive antenna, a patch antenna, then I have to reduce my output power. I will be allowed to radiate only 10 dBm. And if I use even more directive antenna, like a long dipole antenna with 9 dBi of gain, I will have to reduce even more to 7 dBm my output power, the output power of my chip. So this is not so good, because usually when you are using directive antenna, you are thinking that you can increase your range. In fact, it's not really the case. And think that if you are using a miniature antenna, so if you are using a very small antenna, usually you have a lower efficiency. So your gain can be negative. And in this case, then you're allowed to radiate more. Meaning that if you take this miniature antenna with -1 dBi, you are allowed to radiate up to get an output power up to 70 dBm. One very important point is effect of terminal chassis. So usually you have two main family of antenna. So you have what I call dual pole antenna, meaning that you have two parts of your antenna which will contribute to the radiation electromagnetic wave. So you can see here you have a very simple dipole which radiates horizontal wave. Okay, and the second family is the monopole. So, for example, you have the quarter wave monopole, which is well known for this. So you have to imagine that to switch from one antenna to the first antenna to the second antenna, you are using a ground plane. So a ground plane for electromagnetic is like a mirror. Okay, so imagine that if you place a mirror just in the middle of the dipole, you have the quarter wave monopole. But to have this mirror effect, you need to have a very large ground plane. So usually we say that you need at least 2 wavelengths. So 2 wavelengths meaning that it's the size of the ground plane, larger than 70 centimeters. So most of the time, I mean, for example, if you are using a car, you have this size. But most of the time, your device is not acting like a monopole. It's acting like a dipole or dual pole. So of course, the classical dipole antenna is a dual pole antenna. But if you take a small terminal with a short monopole and a terminal, it's a dipole antenna. It really has the radiation pattern of a dipole. And if you are using an integrated antenna, it's also a dipole. So one part will be the antenna, and the second part will be the chassis of the terminal. So to illustrate this, so this is a design I've done for Abiway company, which is an antenna that mixes LoRa and GPS. And in this simulation, I change the size of the device, but I keep the size of the antenna constant. Okay, I just change the size of the ground plane. And you can see that when you change the device size, the total efficiency of your antenna, both in LoRa and in GPS, is changing linearly. So of course, if you have a larger ground plane, you have a better efficiency. So just to show you that it's really the ground plane that is making the radiation of your antenna. Okay. Effect of environment. Antennas are strongly influenced by the close environment, as I already told. And for example, when you are designing your system, you have to take into account all the components which are around the antenna. So for example, the battery or the terminal casing are very important. For the same antenna, we look at, okay, you have in the red, it's the PCB without nothing. Okay. If I add the battery, you have the blue curve. So you see that we switch the resonance frequency. And if you are adding the casing, you are even switching more the frequency. So of course, if you want to cover the 900 MHz band with good performance, you need to be very careful in your design and take into account everything. And for example, the battery, you have really to be sure about the position and in the casing to have something very, very robust. Then in the environment, you have what you can master, which is, for example, the battery of the casing, but you have also what is around the antenna. So if you take this type of small terminal, it can be placed, it can be held by hand, it can be placed on a metallic table. And just to show you, if you move from the optimized curve, for example, I hold this terminal, you see that the resonance frequency of the antenna is shifting a lot. Why? Because the end has a very high permittivity, and it's modifying the field all around the antenna. And even more, if I put this device on the metallic table, I'm completely losing my bands. So it's still an open question how you can solve this issue. So antenna measurement. It's very hard to do measurement of miniature antenna. So, and especially, I discuss with a lot of people who are trying to do measurement in non-anechoic environment. So, anechoic environment is the idea that you will have a room with absorbers in all the room, so you will have no reflection. Okay, so when you are doing measurement in a real room, you will have a lot of reflection. It's very hard to extract useful data from this. And also, it's very hard to measure because you cannot use cables to feed your antenna. Because cables will, a little bit like we saw on the first example, you will have current on the cables and you have parasitic radiation. So the only way to measure miniature antenna is to use total radiated power measurements, meaning that you will put your device in a continuous wave mode and you are going to measure the power which is radiated by your device. So we can move to the open source project. It's in the it's a LoRa collar for cattle roasting application for emerging country. So the idea was to design an open source integrated antenna, and the idea is to get something very cheap and very efficient. So to reduce the cost, the first thing was to say, okay, we have to remove the RF connectors because, of course, you have an additional cost to use connectors. Then you have to avoid external antennas because external antennas, you have also a cost. It can be from $2 to $8. And to do the integration, you need a PCB. You need a printed circuit board. So just the cost to just add an extension to make the antenna integrated on the PCB is negligible. So it's a very most cost-efficient solution to associate the antenna with a LoRa module. So to make this design, I use the logo of my university. So this is why you can see here the PCB. The antenna is really the logo, the UCA letter. Okay. So in fact, I connect the letters smartly to get. You can see you have a sort of. So the feeding is here, and you have a sort of meander. Okay. And in fact, you have a top line, and when you are changing the length of this top line, you can also tune the resonance frequency of this antenna. So basically, it's an inverted F antenna. So it's the PCB is 80 by 34 millimeter. It's on the 8.8 millimeter thick classical PCB substrate, and the performance are equivalent to a classical printed antenna in this area. So here is a simulation. It's matched to 50 ohm. You have a 30 megahertz bandwidth. You have a radiation efficiency of minus 1.2 dB, 75%. And you have this dipolar radiation pattern. As I told you, it's a dipole. So you have 2 dBi peak directivity and close to 1 dBi of peak gain. So just to show you, this design is not magic. You can, if you look at the total efficiency and reflection coefficient versus frequency, you can see that you can cover only all the European, all the US bands. You cannot cover both because it has limited bandwidth. So of course you can tune it, but you cannot use the same device to cover the both bands. So, as I already told you, you can tune the top line, and if you change the top line, you can tune the antenna from 845 megahertz to 950 megahertz. So this is an example simulation. You see when I change the line, you can tune the frequency. So this is reflection coefficient, and it is the same if you look at radiation efficiency. So I compare this antenna with on-the-shelf antenna. So I select some classical antenna that you can use, so a short monopole, a quarter wave monopole, and a half wave monopole. And you can see that all these antenna, this integration, are larger than or longer compared to this PCB. So I do some measurement on SATIMO station to measure the performance of this antenna. So, and okay, you have the result here. So you can see that we have a total efficiency of 75%, 76%. So it's comparable to the small monopole, but the antenna is smaller. And of course, the best antenna is really the quarter wave. Quarter wave is 170 millimeter, but it's 2 times the size of this PCB. And you have also the results for the half wave dipole. And you can see that it can be quite disappointing to see that it has a lower efficiency compared to the other antenna. So it's a dipole that you can buy with on the IMST website. And it's mainly explained because when you have a dipole antenna, you need a balloon to do the imbalance to balance conversion, and then you are losing some power. And so, as I told you, this design is open source, and I have a GitHub with all the layout and Gerber, and you can just use it and copy paste. And promote my university, by the way. So the second project I'm going to present you is a more industrial project. So this is this device. So this device was made with Abiway, Flex, and Orange. So the specification was to get LoRa, so 868 or 915 megahertz bands, Wi-Fi, BLE, and GPS. Okay, and the terminal size has to be 50 by 28 millimeters square. So what we proposed for the solution was to use a dual-band LoRa GPS antenna and to use a switch SP40 to switch between LoRa, RX, TX Boost, or GPS, and to use a separate antenna for the Wi-Fi and BLE system. So you can see here the layout. So the antenna is just 13 by 28 millimeters square, and the BLE is 5 by 5 millimeters square. So here you can see the results, so the total efficiency. So you can see that we get minus 4 dB, so 40% of efficiency for the LoRa band, 70% of efficiency for the GPS bands, and more than 70% of efficiency for the Wi-Fi BLE. The radiation pattern is still an omnidirectional dipole, so for the three different bands. And of course, we measure the system, and we find a peak gain of minus 1.5 dB. So if you remember what I told, then you are allowed to use up to 17 dBm of output power. And then you get 0.5 dB for the BLE, and measurement of GPS is very hard because you cannot transmit. So we use a GPS protocol tester, and we estimate the gain to be 0.0 dB. Okay, so it's time to conclude. So what I try to show you is that you really have to take care about your antenna, because your project might fail if you choose the wrong antenna. With a careful design, your antenna can be at the same time low cost and good. And for some perspectives, it's possible to enlarge the bandwidth of the antenna using some advanced matching network. And also to compensate the environment effect, you can use, for example, some switch to switch between different antennas. For example, we are working on a small terminal that whatever the position of the terminal, you will always keep the vertical polarization, which is very important when you're doing geolocation using difference of time of arrival. So the end of my presentation. So here we have some reference. Also, my presentation is on my GitHub. So if you want just to look again to some slides, yeah, you can easily do. And thanks a lot.
Thank you very much, Fabien. Any questions for Fabien? Don't be shy. It's in the back. Yeah. You can see him from there, or?
Yeah.
Hello, who are you?
Hello, I'm Pierre from Geneva. I have a project and I would like to put an antenna into a back frame. So I don't know which is a good idea, and how can I choose a good antenna?
What do you mean back frame?
A bike.
A bike frame. Okay,
The
the bike. Okay, the bike is not an easy task because the bike is mostly metallic.
Alu ou carbone.
Yeah, but it's metal. So metal is a conductive material. So and imagine that in your project you want to be sure that it cannot be removed.
Yeah. So I test it and it's work.
Okay.
But I think I lose
So you're
a
using
lot of
a quarter wave or just a monopole antenna?
I put the antenna inside and I have my gateway outside and I can make the communication so
Okay.
I can get the data, but I stay close to it.
Yeah, pay attention because with LoRa you have so good sensitivity that when you are close to your device, it's always going to work. Then you have to look at when you are going longer if it's still working. And usually, you really place inside the tube of the bike?
I don't have the bike, I have tube.
Okay.
And tube like this, and I put inside and I close both face. But no, it's working. I don't know how far it's working.
But it's working at maybe 100 meters.
Maybe.
Yeah.
So now my question: how can I choose?
You are doing a Faraday cage. So if you are enclosing your antenna inside a piece of metal, I mean, of course, a few part of the power can exit, but just a few parts. So you are losing a lot of communication range.
But there is a way to choose, even if it's not be the best solution, to choose a good antenna. Or,
I mean. Practically, there is no solution if you want to place inside the bike tube.
Perhaps a stupid idea, but can't the bike itself be an antenna?
Sorry?
Yeah, this is...
Can't the bike itself be an antenna?
One nice solution would be to use the bike as an antenna, because if you can
we use
the bike can...
it's
possible, yeah.
Oh, look at that, problem solved. It's you again. Hello.
Hi. So I have a question for perhaps recommendation for maybe a small hardware startup designing a product with a PCB antenna. Obviously, VNAs to design good matching circuitry are tens of thousands of dollars. I mean, Agilent ADS software package is 50 grand and above. So what are your recommendations for?
I mean, VNA is useless for miniature antenna because VNA you need a cable to connect your antenna, and then the cable is going to influence a lot to change the characteristics of your antenna, and you are not going to measure the behavior of your antenna without the cable. So VNA is not really used, but the best solution really is to put your module in emitting mode, so in continuous wave mode, and to use a spectrum analyzer to measure the output power in different direction. So of course, if you can have access to some anechoic chamber, it helps a lot because. But then if you are outdoor, for example, and very careful, you can have quite good results. I mean.
Right, but you can't design a matching network with just measuring the output power.
Okay, of course. Matching network, of course. If you need to mix matching network and antenna, it starts to be not easy. For my side, when I'm designing matching network with miniature antenna, I go to simulation. Because really, I mean, if you try it, you will see you connect your antenna with a cable. Just pass your finger on the cable, and you will see the resonant frequency of the antenna moving very fast. So because there is a lot of current on the shield of your coax, so measurement of miniature antenna is really hard.
And the software for simulation is also very expensive.
This is, yeah.
So there's no solution.
No easy solution. I know that, for example, in Switzerland, there is a company, Spiag, that gets some solution to measure input impedance of antenna using optical fiber. You know, so optical fiber, you get a galvanic isolation. Mm-hmm. So you don't get the shield of your cable, and then you can measure it accurately.
Yeah. Thank you.
Okay, thank you. We have another question right over here. Hello, who are you?
I'm Steve from Milano. We saw that antennas are influenced by the surroundings. Is this true with plastic casings as well?
Oh yeah, the plastic. This is the example I show on the, I think here, the plastic casing. This one, no, this one. You see here, when it's between the blue and the red curve. When you are adding the casing, I mean, if you compare the blue and the red curve, I mean, the difference is very important.
So plastic is not transparent?
No, plastic has a permittivity different compared with the air. So it's usually 2.7 or something like that. So of course, when you put plastic close to your antenna, it's moving the resonance frequency.
Okay, it's time to round up. But I have to mention, Fabien, that if I count the heads right, this was the most popular talk of today. So congratulations with that.
Thanks a lot.
Okay.
Thanks.